Hello, everybody. Thank you so much for tuning in to this episode of Alien Astrobiology Lessons for an Interdisciplinary Education Network. We are so excited today to be hosting a programming and machine learning expert. But first, I'll introduce myself. My name is Ariel Aslan. I'm a student at Arizona State University. I'm studying biomedical sciences and data science, and I'm here with my co-host.
Hi, I'm Trey. I'm also a student attending ASU, and I'm studying astrobiology and biogeosciences.
Awesome. And today we are so lucky to be interviewing Dr. Ryan Meuth. He is a teaching professor at Arizona State University with expertise in science and engineering education and machine learning. He received his bachelor's, master's, and doctor of philosophy degrees in computer engineering from Missouri University of Science and Technology. He currently serves as a member of the first-year programming teaching team that develops and supervises all sections of CSE 110, Principles of Programming, and CSE 205, Object-Oriented Programming and Data Structures. Lucky enough to take both these classes, and they are awesome. So thank you for being here.
My pleasure.
Awesome. So let's sort of get into the discussion today. Our first question for you is, can you explain why programming languages are languages in the first place? How is communication with computers similar to direct communication between humans?
So, computer programming languages are languages because we're human, right? So, and kind of on the topic of your podcast, the computer itself thinks in a very different way than we do, right? It is logic and math, and that's it, right? So we've had to figure out patterns of working logic and math together to develop and translate between things that we want to do and the way we want to express it to how the computer can understand it fundamentally. Because understand is a big word that doesn't really mean anything, but because the computer just knows numbers and voltages, right? It is just a machine. So saying something like, I want to repeat this loop 1,000 times and inside of it make a decision. And when this happens, do that. And when that happens, do that. That's what we want to be able to say, right? So as humans, I want to communicate that to this machine and have it do that work itself, right? The first programmers, the first developers wrote directly in binary, which is the only thing that the machine understands natively, right? And that was very, very challenging because we have to do all of the translation steps to get down to it. It's like, I'm doing a bunch of math. I'm thinking about how is the computer going to execute it immediately, how all of the hardware works and interacts and stuff like that. But as we were doing that, we were learning, oh, we keep seeing these patterns for useful things that we do all the time. So let's invest in a huge amount of energy to write a program that translates from something that's a little more human-like to something that the machine can understand natively, right? And those were the first compilers. And all the compiler does is translate between a human language-ish to the machine language that the computer can execute natively, right? And those people were crazy, like Grace Hopper and some of the early computer scientists. They didn't have a high level language to write this incredibly complicated program with. They wrote it in machine language or at best in assembly, which is basically just like a thin layer of a higher level language on machine language. And they had to do this immense amount of work. But once they had that first compiler, the second compiler was a lot easier. And then it opened it up to everybody else. So computer languages are there so that we can express ideas and concepts to the machine that allow it to execute it, and we get to make it do whatever we want.
Yeah, that's cool, especially considering the classic teacher joke, which is my computer's saying what I told it to, not what I want it to.
Yeah, yeah.
Which is cool because I don't know, programming is very, like, there are levels of fluency, and there's, I mean, the name of the game is efficiency. And as you just make your program more and more efficient, it just becomes better and better, and you're able to like directly communicate with the computer about what it is you want and how fast you want it.
Yeah, totally. And the higher you get into it, the more you learn about like computer languages co-opt a lot of what we say about human languages, right? Where we talk about syntax, right? And that's how you structure a message. We have like style and grammar when we're talking about, maybe the tone that we're using in a human writing or a human presentation or something like that. Um, we have style standards for code, and what these are actually for, rather than being for the machine, because the machine doesn't care how we write, right? After the first level of translation, all of the variable names and the method names are stripped away, and there's just like a generic concept of like, this is variable number one, and this is what type is associated, variable two, and type is associated. It's all memory addresses, right? And then, what those standards are for are actually communicating between other people, right? So it's not about, when I'm saying like, I want all of our variables to have like descriptive names and use this format, and tabs are 5 spaces, or indentation is 5 spaces, not tabs, stuff like that. Those are for other people, not for computers, right? So these programming languages and the standards for communicating with them are as much more, sometimes it's more for, I am working with someone else on this large program, and we need to agree on how we're going to communicate together and how we're going to work together on this. And then also how we can communicate effectively to the computer.
Yeah, so like two levels, two different entities that are receiving your message. Yeah, that's really cool. I feel like that kind of goes into your question, Trey. So I'm gonna let you take it away from here.
It does kind of perfectly, actually. So what I was gonna ask, which does kind of segue off of that in a lot of aspects, is that in a lot of like sci-fi books that I've read or movies and shows that I've watched, it's a common trope that when we do find or meet aliens, we communicate with them not through like language or through like instead, we like connect our computers and exchange information that way. But it got me thinking, and I was like, so how likely is this? Like, is it really like safe to say that an alien civilization would build a computer that would be even remotely compatible to how ours work? And I guess like the main point of the question is like, how many different ways can you build a computer to the point where they just can't connect?
Right. Um, that's a really interesting idea. The biggest challenge. This is sort of tied to the question that Ariel sent me that I think comes next. But it's computers are a manifestation of math. Like all of our computer science departments at universities that sort of did all of this stuff came out of math departments, right? Because they were building machines to help automate mathematical processes, right? And that's our sort of way of working with computing and things like that. So there are all of these like they do math the best, and they started with math, and all of our foundations are in math, right? Um, there are a million ways to build a computer, right?
Mhm.
There are more than a million. There are infinite ways to build a computer, right? Because the rules for building a computer are very, very flexible. And we talk about like a Turing complete machine, and it's a machine that no matter how you build it, you can feed it some instructions, and it has some properties, and um, it can compute and follow that set of instructions, that algorithm, to come up with a result of some kind, right? And as long as you can, and there are some proofs in math about, if you have a machine that has a certain quality of capabilities, then it's Turing complete. And no matter what the language is, or how you express it, or how you write it down, or anything like that, if you can, you should be there. It is absolutely possible to translate an algorithm in for one type of computer, as long as it is also Turing complete, into any other computer language that is also Turing complete, right? And they've shown this is true. You can, we use, like electrical signals and binary for our computers, right? That is what we found to work the best, right? There are water computers, there are mechanical computers, right? So instead of electricity, we mediate computation using like fluids. Instead of voltages, we mediate computation using gears and cogs and like mechanisms and stuff like that. They're working on so they're working on biological computers, right? That use molecules and organic materials to make computing happen, right? All of these things are different ways of computing, but because there's like this, the at least my impression is that because there's this like fundamental thing of like it's not really a computer unless it can do these things, and if it can do these things, then we can have a translation layer between them, right? But that translation layer itself is an incredible engineering challenge, right? Like how am I going to have, if we're gonna, if people that if we meet, we're out among the stars, we meet people that evolved in an ocean or something like that, and their fundamental medium is like chemicals or water or something like that for computation. Translating between our binary systems and their chemical and liquid systems is going to be an immense engineering challenge, right? It'll probably be easier to just go down to the math fundamentals, right? Because like communicating across initially, even like how can we even plug our two systems together? That'll be a massive communication challenge, much less like getting them to talk to each other and stuff like that, right? So we'd have to bridge that communication gap before we can start to plug them together. It might be, in that far future that we can, just have our AI work on it and it figures it out or something like that. But the the Independence Day scene where they like upload the virus into the computer or something like that.
Yeah.
Yeah.
Just it cracks me up every time.
Because I've always watched that scene. I'm just like,
Yeah.
that would like theoretically only work if their computer systems like operated exactly the same as ours.
Yes,
I was
absolutely.
like, look, what are the odds of that happening?
Sorry, I can we pause for just a minute? I'll be right back.
Yeah,
Okay,
no worries. Trey, that question is so good.
thank you.
That's funny about that scene. I actually haven't seen that movie in a bit.
Yeah, it's like that movie's pretty great, apart from, everything that it does bad. But one of the things that it has also always cracked me up is the whole they take down everything with a computer virus. I was just like, nah.
Yeah,
I,
little
I,
bit unbelievable.
yeah, like you mean to tell me that they're advanced enough to travel across the galaxy to our system? And one, their method of getting rid of us was invasion, which is, the most ineffective way of removing something.
Pretty
But
sloppy.
yeah, but it's also we are able to take them down because of a simple computer virus. Like, even if our systems were compatible, they ought to have like what's it called in programming? Where like it like goes through and removes viruses. What's it called?
Antivirus?
And yeah, they have to have antivirus systems that are beyond our understanding. that would just immediately get rid of anything we tried to add to the system. I
That
was just
does,
like,
well, it's an interesting question of like, if you're advanced in other areas, like, do you have to be advanced in computing and technology? And I would say like, yeah, but I don't know, it's kind of interesting.
I don't know, the argument I guess could be made because like despite what people tell you, like a computer that you would need like on like a spaceship to travel anywhere, not just between planets, but also between stars, like it doesn't have to be all that complicated. Like,
Hmm.
in all those books, movies, and stories where there's like a spaceship with an advanced AI system that's used to run complex calculations, it's like that's kind of unnecessary if you think about it. So I guess that could be the case.
Yeah,
That they just weren't very good with computers because they never had a reason to be.
right.
Especially with the
There's,
species that's telepathic, so they never really had a communication problem. Or,
yes.
yeah.
Remind me, we talked about Dune in our sci-fi episode, but like, are you super familiar with Dune?
Yeah.
Okay. You know about the Guild Navigators?
Those are like the people that take the drug that expands their mind or something.
I'm having to look this up actually on Dune Wiki.
Ah,
So,
not a true
um,
fan.
I know. I only read the first book. I'm sorry, Frank Herbert. Uh, I want to read the others. Okay,
That's one more
so
than me, so you're doing.
a guild navigator was a senior rank of pharmaceutically enhanced humans within the Spacing Guild. So yes, yes, Trey, yes. Physically transformed through the consumption of massive amounts of spice. They utilized a highly conditioned form of prescience to safely cross interstellar and intergalactic space in colossal starships. So, the reason I brought this up is because this isn't necessarily like a computer, um, but an organism that is sort of acting the role of the computer, um, in what we would kind of like, assume a computer to do on a super cool like intergalactic space mission like these. Um, so let's see. To maintain their prescience, navigators not only consumed large quantities of melange, which is spice, but lived in rectangular anti-gravity tanks filled with high concentrations of orange spice gas. This level of extreme and extended exposure, coupled with years of microgravity, caused their bodies to atrophy, mutate, and elongate over time. Oh my gosh, that's really cool.
So they're fleshy abominations and floating in a fish tank in the
Yeah,
middle of starships.
yes. Um, No, yeah, there are some crazy pictures of like art.
Bizarre way to go about interstellar travel, but okay.
I like how creative it is.
Yeah,
Um,
because he wanted like a way like to incorporate so that they could have interstellar travel because regardless of what you think, you still will need some computer power, but he also wanted to be like, oh, but there is no computers because there was like an ancient war with AI or something that they like
yeah,
abolished like the use of computers.
yes. The Butlerian Jihad, I think it was called.
Yeah. And I think that that's a pretty interesting take on like the situation that he created. Like that's a pretty cool way to go about making sure the universe still like that he created, like in his book, like still
Yeah,
works without removing this one key important concept. Which
yeah, I agree.
yeah.
There's a cool quote at the beginning of the book. Let's see if I can read it.
Whip out your book and start quoting directly, like page nine,
I know,
line
right? I,
two.
I wish I had that book here in my dorm. Um, let's see.
Yeah.
Let's want to find it.
Well, I guess while you're looking for that, I really got excited for that question I asked because They actually talk about it in great detail in Children of Time.
Okay.
I don't want to spoil too much, but I'm pretty sure you already know, like, because you've told me about like the ant computer.
Yes. Yes.
Yes. So I was like, basically one of the tropes in the second book, but it's only like brushed over. It's just like, oh yeah, they figured out how to do this. End of story. They started incorporating like spider ant colonies into human-based computers to kind of like, well, to know, make their computer systems compatible for both species. So that's
Wow.
essentially how they talk to each other in the second book, right?
Yeah, so like a computer is a translator, which is
Mm-hmm.
so
So,
cool.
but my thought was like, how do you convert the human's semiconductor one zeros and then ant pheromones? Like, where's the bridge there?
I think that's where it gets so cool because the bridge is obviously your base language in the universe, math. And
Mm-hmm.
it you know, math is the basis of physics, is the basis of chemistry, which is the basis of biology, and
Right.
biology and chemistry work together to produce pheromones and like I don't know, it's just so cool.
Yeah.
Yeah, it makes me like, oh, I love it. Okay. Still just want to find a preview because of the book because it's in the very first pages.
Okay, sorry about that.
Oh, hi, Dr. Meath. You're
Welcome
good.
back.
We were nerding out about Dune and children while you're gone.
Awesome.
Okay, well, I guess to kind of get into that next question that you were alluding to, um, how could learning a language based on logic assist with communication in other areas of our lives?
I think the it's a fundamentally it's a sort of like sequential way of thinking, and it's a sort of abstract way of thinking, right? Because you have to model. Normally, when we're communicating with other people, right, we have some idea of what it is we want to communicate, and we have some idea of how we have some idea of the other person, right? So the a lot of what human communication is I know, this person, Ariel, you're a student at ASU, you're studying in a different discipline than I am, but we have some commonalities in that you've taken a class with me, so I know that you have a baseline set of like language and vocabulary that I can, you know, say stuff about, how programming works and stuff like that. And that's a place where I can start building, and I can say, I can define new terms in terms of old terms, and stuff like that. And we have a common language that we share. And my guess is you're from the United States, so we have a common culture that we can build on, right? Um, Computers are fundamentally human alien, right? They're designed by people, but they don't have any of that. They don't have a culture. They don't have a common language, but we've built a common language to translate between us, right? We built an intermediate language to translate between us. And but going through the process of learning to program and learning the logic and the problem solving process and stuff like that builds up um, a set of like tools that you can use to more communicate effectively, right? Because now I can, it's a lot of systematic thinking of like, this is a sequence of things that I need to do to build up to a solution to a problem, or get the computer or the robot to do whatever it is that I need to do, right? And that's like sequential and logical thinking process um, has a lot of advantages for business communication, and it has a lot of advantages for like starting new communications with like other people, or people that you're not familiar with and stuff like that. It also has some advantages in that it's a set of new analogies, right? And in that it's a you know, we talk about like loops and repetition and methods and classes and objects and all kinds of stuff that allows us to abstract away some fundamental concepts in a very, very low level way, right? Especially when you're working with math and you're talking about like mathematical concepts and things like that. Those are things you can go to think about things in a different way and talk about things in a different way, in that you can express it. Like if you both know about these two ideas, then you can say, oh, this is like um, I don't know, it's like integration or something like that. And you have an idea, oh, this is a similar process to whatever we do when we do this thing called integration, right? And that allows us to sort of level up our language with abstraction in a bunch of different ways. So I think like learning a programming language changes how you think and how you approach things. And it also gives you other tools that you can use to communicate in different ways to people that have similar backgrounds.
Yeah, I totally agree about the changing the way you think thing. I was pretty surprised when I started taking programming classes about how it did, like, literally start to change,
Yeah.
like, how I think. And that's a big argument I use if I'm sort of like gunning for like an internship or something, where I'm like, hey, like this internship uses a lot of programming. I really like to program and like I have programmed, so I can think in that way. And like I
Hmm.
think that's a commonality that me like and you, the person who's reviewing my application, have with each other. So let's get there, you know?
Yeah.
So I think it's pretty like I would love for every student to be able to sort of have like a little bit of coding experience just because it is so cool to like try and think about a problem like purely logically and with efficiency in mind.
Yeah.
Um, when you say it, like the computers are human alien, I just think that's so cool because one of the questions in astrobiology is like, have we created life? Like, have we created uh like life
Mm.
here on Earth, new life? Because the whole thing is, oh, we're looking for new life. We're trying to define what life is. We're trying to see what new life could could look like so that we can detect it. And then
Mhm.
the question is like, well, have we created that here on Earth? And like I always think like, you know, with computers, I don't know, it feels very alive in a sense to me. So,
I think we're really getting there.
yeah.
Like especially with the advent of AI. And so like life in computing is really challenging because we can use a computer as a substrate to simulate life. We can use a computer as a substrate for computation that supports consciousness or a different organism or something like that. But there are things out there that are like equivalent of, you know, we talk about viruses and worms, right? Those are programs that self-perpetuate, they adapt to their environment, they don't evolve necessarily on their own, but they live in the world, right? In much the same way that like a biological virus is a kind of computation that is mediated by molecules. It doesn't necessarily, it's maybe not alive, but it might be. And it, you know, uses the infrastructure of, you know, other cells and stuff like that to perpetuate itself. And we kind of think like maybe that's alive and maybe computer viruses are alive. But on the other side of scale, you've got things like these new agentic AIs and things like that that are doing things that mimic life processes, but they think in a completely different way, right? Like our neural architecture and stuff like that is built for um, mainly like predation, dealing with predation and dealing with sustaining a biological system and sustaining a species, right? It's fundamentally grounded in like perception and events, and like we've got this lizard brain that is watching for like snakes and spiders and all kinds of stuff like that, right? The way that it's architected is very different from what we're building as intelligence, which is much more, it's like we came up from like bugs and lizards and stuff like that, and our neural systems were built on those systems as they evolved, right? So the stuff that's built in for those is like, is that something I can eat? Is that something that's going to eat me? How do I find someone to perpetuate my species with, right? Those are the fundamentals for us, right? And then language happened to happen somehow because of that, right? AI is starting with language and then building down to those fundamentals when we put them in robots and stuff like that. So it's a drastically different way of thinking with symbolic and abstraction as the fundamental, rather than like, is that blue or green? Is that moving as the fundamental, right? So these
Wow.
things that we're building, we're meeting them in the middle because we have a language that we share, but fundamentally their neural structure and what is the fundamentals that they're built on is totally different. And they're alien to start with, but they feel familiar in the same way. It's very, very weird.
Yeah. And, like the, wow, yeah, their neural structure is very different and it's like fundamentally higher level, I think. So that's, if you think about like the science fiction idea of machines like replacing us, that is sort of like an interesting
Yeah.
interesting topic. Kind of scary, kind of cool. Um, but yeah, I guess that also flows into another question, which is math is often cited as the universal language that would be the best to use with theoretical alien civilizations. We've kind of talked about this, but would you consider programming to fall under that math umbrella, or is it something different entirely? Is it both?
I think programming is a manifestation of math, much like physics is kind of applied. The mathematicians will say that everything is applied math, right?
Mhm.
So
Yeah.
like physics is applied math and chemistry is applied physics and so on and so forth. Um, computation, computing, programming, stuff like that is very, very close to math. A lot of what we use to figure out algorithms and algorithm performance and how the machines work and stuff like that is all based in symbolic mathematics, discrete calculus, and all this stuff, right? All of our theory is based in mathematics, and all of computation came out of math departments, right? It didn't come out of like chemistry and physics departments. The mathematicians were like, we want to solve problems that are really hard, and it's taken us a long time to do them. Let's see if we can build a machine to do it, right? And they had analog computers to start with, and then they started building digital computers that could do sequential. So like an analog computer is like setting up a system of equations in either a mechanical system or a um, uh, either a mechanical system or an electrical system. But instead of in an electrical system, instead of having ones or zeros and it being digital, you can have a varied voltage, right? And it's the mathematical equivalent of setting up a system of equations and giving it initial conditions and then seeing how it evolves over time, right?
Mm.
And you can get a solution by setting them up smart. You can get a solution to whatever problem you're working on, but it requires custom hardware for every problem that you're working on, right? And they're like, this is taking too long for us to do. It's really hard to build something that's general. So these guys came along, mainly Turing and von Neumann and stuff like that, are like, okay, let's build a general purpose computer, and what is required, what is the simplest possible thing that we can do to make that to make computation happen, right? And they came up with a concept of a Turing machine, and then they figured out how to translate it into a physical thing, right? Applying all of this other engineering stuff. So computation is fundamentally mathematics from our perspective, um, and yeah, and we I don't know if I buy into the idea that math is universal. I think the way everything that humans create and have created is biased by this, how this developed over millions of years, right? And where there might be completely, if you if we grew, our species evolved in um, savannas and prairies and in the ice age and stuff like that, and it's all, like based on land, and all of our analogies are around pursuit and stuff like that, right? We have a way of thinking that is biased in a certain direction, right? And that goes way, way back, and all of our math, all of our science, and all that kind of stuff might have completely different ways of thinking about it. If you're a species that grows up in an ocean, or you grow up in, as like a in like the clouds of Jupiter or something like that, these environments are fundamentally different, and your way of thinking about the world and perspectives on it might be fundamentally different, right? Terrestrial, growing up on the ground, intelligence is going to have a different set of biases and perspectives than whatever we might see out there. So I don't know. I don't know if our math is fundamental. Maybe capital M math, if it exists, is fundamental. But maybe it's a place to start, and we can, maybe we'll have some overlap. It's the our best idea for being able to overlap with someone else.
I think it's a very good distinction, our math versus capital M math.
Yeah.
Trey, do you want to add anything to that? Because I
I
feel like you have a
did
lot.
actually. Because you did say like how our math, or math as we understand it, might not be fundamental, and it got me thinking, and it is back to like a whole lot of books I've read. One of the things that's very common, like when the humans in the stories are trying to talk to these aliens, is trying to develop like a language, and they start with math. Like, are you familiar with Andy Weir's Project Hail Mary?
Yes.
Yes. So one of the things that he tries communicating with this extraterrestrial is like what numbers were, but they ran into the problem that humans counted in base 10 while the Iridians counted in base 6. And I was thinking like, wouldn't math as we think about it just start completely falling apart? Like none of our equations that we have made would work in a base 6 system.
That
Like
is not correct,
it's
right?
not correct.
It is not correct. So math is independent of base,
It
right?
is.
Because
Okay.
it's all you're doing when you define a mathematical relationship is define a relationship between two quantities, right? So it doesn't matter if I'm using base 10, or I'm using base 6, or I'm using base 2 in binary, or base 8. There's an amazing book series. It's called Rendezvous with Rama.
I've read that books.
You've read that book? Yeah.
Yes,
And
sir.
they have the spiders, right? And they have octal instead, right? Because they had 8 legs, and stuff like that. And they're um like these different ways of thinking are still grounded in quantities, right? As long as you can say like, oh, let's define, the fundamentals of algebra are based on set theory, which doesn't really care how many of anything you have. It just says like, here's none, and then we can, if as long as we can define none, we can define one, and once I have that, I can define an operation, and I can define any number, right? And it doesn't matter how I represent that and how I write it down, the relationships hold after that, right? And this is sort of their argument for math. It's like, if I can communicate our rules, a set of common rules for doing mathematical operations, then we can like extend that and communicate relationships, and then maybe communicate something that's more complicated.
Yeah. And to just expand off that, have you read Contact by Carl Sagan, or are you familiar
Absolutely.
with that? It's
Yes.
they, they do that exact same thing with the alien signal.
Yeah,
They realized that the aliens were sending them a bunch of math problems to start building a baseline for more complex information. So, yeah, that actually makes a lot of sense.
yeah, yeah. Because once it doesn't matter. The representation doesn't matter, right? Because the math relationships still hold, and as long as you can build a translation to your representation, then you can start to read it, right?
Yeah, I think that's where that idea does come in, you know? Like capital M math is just like governs our universe, so therefore any being within our universe is going to like at a certain level of intelligence is likely going to base something off of it. So then we can find that connection point that we were talking about.
Maybe,
Maybe.
right? Maybe,
Okay.
right? And it's our best idea for it, right? Because it seems like, oh, like we can drill down to those fundamentals. Like I took the last college class that I ever took for my PhD program was a it was an algebra class, but it was foundations of algebra. So it's like, how do you build math, right? And and it was like, here's set theory. The idea you have this incredibly abstract idea of this is a set, right? And you start with this is an empty set, and I put basically a circle around that and say the empty set, the size of the empty set is one. There is one empty set. Now I have the concept of one, and I have the concept of an empty set, which is zero. And now I can literally build everything else. And we did that for a semester, right?
Wow.
And and it and it was fascinating, but it was also incredibly brain breaking, right? It's just like, how do you, I'm literally standing, all of our math literally stands on the concept of nothing, right? And all we did was put it in a box and say, now I have one. I have nothing, and I put it in a box, and now I have one, and then I can count to the rest of the world, right? And that feels very shaky, but it seems to work, right? But that fundamental idea of this is set theory and stuff like that is rooted in our wanting to hold something, right? It's an object. It is, I can put a boundary around, right? Like I imagine a alien civilization that is, I don't know, like smart gas or something like that, right? That maybe doesn't have a concept of boundaries or something like that, and that all of their thinking is analog and degrees and um, like more or less. Maybe it's defined in relatives or something like that. And maybe we can get there. We can find something that overlaps in our language or something like that. But starting from fundamentals, if the fundamental concept is super different, right, between us, then maybe it's going to be really hard to make that to build a set of rules based on something that we have in common. I think of the
Well,
aliens from Arrival,
yeah. Yeah.
right,
The
Yeah.
and stuff like that, where it's so fundamentally different that it takes a huge amount of effort to start like parse it, right?
wow.
Yeah.
That's so cool. My brain is expanding as we speak, guys. Trey, did you want to add anything to that topic before we
No,
transition?
I just got excited when you pointed out rival. I was like, yes. But I did really like the point you made with like, what if an alien civilization we do run into is like just so different from us, like an intelligent gas cloud. Like their idea, I could imagine, of like math would be like, it would be less like discrete or foundational, like not ones and zeros, but maybe like quantity, like you said.
Mhm. Yeah. But
And
and not even a countable quantity, right? Maybe it's
mhm,
just relative or something like that.
exactly.
Or oh, what are they I can't remember what they called the aliens in the like Ender's Game series, but they were
Oh, the
fundamentally
buggers?
the what?
The buggers, I
Yeah,
think.
the
Something like that. Yeah.
I don't know if that was
And
just a derogatory term for them,
I thought
but
so too.
yeah.
I know they had a name, right? But the but they were swarm based, right? So the individual doesn't count as much as like the super organism, right? So like how would we communicate with a swarm of bees, right? Or a swarm of smart bees or something like that, where the organism is not, you know, something
Mhm.
that it has a boundary necessarily, right? It's something that
The
changes all the time.
organism that you're like talking to isn't the intelligence, it's just the small part of it.
Yeah,
A
yeah,
cog.
also true. Yeah.
Yeah. Wow. I think that also, I don't know, talking about math in general definitely comes back to this sort of foundational concept of our club, which is that like interdisciplinarity really governs astrobiology and it governs like, space exploration both just in thought and in reality. And, you know, Dr. Meath, you talked about how math is the foundation for um, physics, which is the foundation for chemistry, which is, continues to underlie other things like biology. And like we can see it like stepwise, and then we can also sort of like zoom out and see it as an array of various disciplines that all work together to come up with sort of like how we are now. Like you talked about how mathematicians wanted to make things easier, so they sort of created like programming, and now we have that for every like discipline, and
Yeah.
it makes everything easier for everybody. So like that's pretty cool. I like
Yeah.
that.
Yeah. And something I wanted to mention earlier, and I skipped over it because it's sort of a rabbit hole, is we're still discovering new ways of thinking about both math and computation, right? So like we're what's the new hotness now. I just got back from a conference from it's a uh, um, engineering education conference, but it's primarily focused in the IEEE, which is the Institute of Electrical and something engineers, electrical and electronic engineers. I think that's what it is. But they're mostly focused on this particular conference is mostly focused on like computer science education and stuff like that. And we're talking a lot about AI, and we're talking a lot about what the future holds. And what surprised me is a lot of people were talking about not just AI, but the next big thing on the horizon is the advent of quantum computing, which is fundamentally way different than how traditional computing works. And it's based on fundamental properties that are less about discrete, here's a boundary, and more degrees, here's a quantum state that's
Mhm,
spread over time and space, right? It's more of a probability, right? Rather than a this is a one or a zero. It's like we're somewhere in between, right? And you get all these things to interact, and it's much more like an analog computer, and it can solve some problems that we can't normally do. And that's a one. It's a suit. I cannot think that way. I have not been able to wrap my head around how that works. Besides the most like basic concepts, and so it's a new way of thinking, and it's a new way of doing computation that might have some like massive advantages for us and things like that. So there's in that whole world, there's again another set of these are things that we can do to solve problems. These are ways we can talk about how computing works, and it's a whole nother set of ideas that changes how we can like communicate and relate to each other and how we understand how the world works and how we might be able to understand how each other work.
that's amazing. That's awesome. Um, I guess sort of bouncing off the whole idea that your conference is like imparting on you guys, let's sort of transition to education for the last little bit. Um, what are some of your favorite approaches to teaching?
My favorite approaches to teaching. Um, um, I really like there I'm very biased because the way that I learn best is by doing a thing, right? So I was not a good student in the traditional system. I was okay. I was a good student. I wasn't a great student, right? I was a solid B student basically my entire life. So you know, if I got an A, it was by accident, not by like my personal motivation or anything like that. And the reason why is like I was I had trouble grounding what I was learning in most classes in something that mattered to me and that in increasing my capability. I love the idea of like I want to be able to do something new, right? But doing a homework problem that is like super abstract or something like that didn't like make that connection in my brain. I know that I'm exercising something and that I'm engaging some machinery to make you know solve the problem or something like that. But I didn't have a good path for a good way to visualize like how does this make me better at some goal that I've got, right? So my favorite way of teaching is to say like we're gonna we're gonna make a thing, we're gonna build a thing, we're gonna solve a problem, and on the way we're gonna learn how to use this programming technique. On the way we're gonna learn why we use this programming technique. We're gonna learn you know what are the alternatives and why this one is better than that one and stuff like that. And being able to couch like a concept in, you know, here's a situation where you're going to use it, and here is why we're using it, and here is how to use it, sort of like integrates it with a lot more parts of how people think about things rather than it just being like, you know, these are all the rules for programming, right? And here's a new rule that we're going to slot in here, and we're going to show you how to use it. But recognize the other problem is like this is all for problem solving, right? So like, when do I know when I should use this thing? When do I know, you know, what are some patterns for using it? Stuff like that. Having integrating all of that stuff together is the biggest challenge in teaching um, anything. And I like having it's called project-based learning, and I like having a project to focus on, and then you know sort of investigating how to do that and build up a solution over time. Um, is I think the one of my favorite ways to teach. It is the most time consuming because part of that is like trying and failing and stuff like that. So figuring out how to do that in a semester and in a safe environment where everybody can eventually succeed is really is very challenging. But I think the payoff is high.
Cool. Yeah, I really like that approach as well. And sort of to finish off the interview, if you have some sort of statement about why maybe you'd encourage some of your computer science students to take humanities courses that could expand their knowledge of cultures in the world, since we're all about interdisciplinary education collaboration. Have any experiences in your life shown you that importance? What do you think?
Oh yeah, absolutely. So I I think it's incredibly valuable to gather as many, especially if you're a computer scientist, if you're someone that likes computers and loves, you know, is interested in programming, um, the more ways of thinking that you can gather, the more effective you'll be at building solutions to future problems, right? Not only in like not only in like, you know, I'm learning some stuff about biology because I want to work on, you know, medical health systems or work with medical data or something like that. That's not even, you know, that's the like first level of interoperability. The solutions, ideas, analogies, the processes that show up in all of these different disciplines are like patterns and tools that you can apply to solve vastly different problems, right? And having as many of those different ideas kicking around in your head means that you'll land on something that is both creative and efficient and more and easier to implement. You're more likely to have all of these things floating around, and if you have all these things floating around, you're more likely to land on something that is a drastic innovation and changes the way things work, right? They used to call them people like this polymaths, right? They're people that are, I'm not just one math, I'm, many maths or something like that, right? And they're people that are so intersectional that they can see connections and solutions that can apply to lots of different kinds of problems. I studied, I got a minor in neuroscience in college because I was interested in how do brains work and how do I make smart machines. But the stuff that it taught me about how my own brain works, and it taught me how about other people's brain works and stuff like that. It turns out I was in love with brains, but not so much to make them, but to like figure out how to teach them and figure out how to work with them and stuff like that. And all of that stuff comes together in, whenever you're trying to apply something, you can look at all of these different interdisciplinary ideas and problems and ways of thinking and ways of approaching problem solving and applying those in places where they're not typically applied can have incredibly huge benefits for efficiency. I highly recommend just pursuing some weird classes. Take a film class, take a psychology class, take a neuroscience class. Um, you know, all of those things show looking at how the sausage is made in so many different disciplines gives you so many new tools and it's fascinating, just absolutely fascinating.
Thank you so much, Dr. Muth. We really appreciate you coming on. This was great.
I am so glad you had me. This was really fun.
Yeah. And for anybody listening, tune in for future episodes of Alien, and we hope that you learned a lot. I know I learned a ton, so super fun. Trey, closing remarks if you have any.
Uh, no, not really. He kind of covered all the bases I was gonna try to squeeze out of him. Uh, no, but I did really like that point at the very end that you brought up, like that it's important to uh, I guess expand like what to things outside of not just what you're interested in because it can like broaden your horizons. And I really related to that because a lot of like the prerequisite classes that I've needed to take in college that quite frankly at first glance have absolutely nothing to do with my major. I I've managed to never be upset, disappointed, or hoping that they're over in any single one of them
Hmm.
because I would like go to class and I would do this thing that I thought I didn't care about and was like, whoa, this is actually pretty interesting.
Yeah,
So yeah,
totally.
I liked that.
Awesome.
Yeah, that's awesome, Trey. Um, cool. Well, thanks everybody for listening. I'm gonna stop this recording. I hope all of you tuning in have a wonderful day.